Hello guys, welcome to my video series 5 minutes to geek. Today we will be discussing about linear SVM. Okay, so linear SVM Python implementation. So in the last video we have discussed about what the SVM is, what is the maximum margin classifier, what is the state vector classifier, and we have discussed only the linear SVM in the last video, and today we will be discussing their Python implementation. Okay, let's quickly get started. Here we are basically importing all the libraries which I would be required. The major among them is importing the sklearn implementation of SVM. Okay, let's move ahead. Here I would be creating the model on the data of cancer data. There are basically two types of cancer. One is a benign cancer and malignant cancer. So we will there. I would say these are the two classes of the cancer, and we would be creating a model which help us to classify depending upon the characteristics and various medical results. Help us to classify which type of cancer it actually is. Okay, so let's read the data into the data frame. Let's check out the data. Actually, there are 33 columns which are available. I think the last column is of no use. It's actually have no such significant values available in it, and similarly the ID column is worthless for us. So let's just drop these two columns and now check what is the data frame which is available with us. So we have dropped the two columns and we are left with the 31 columns. There are other various columns which are basically tells about the medical terms like compactness, smoothness, and other things. These basically help us to determine which type of cancer if a person is having. Okay, so let's see what are the various type of diagnosis. Diagnosis basically the end result, that is the M stand for the malignant cancer, B stand for the benign cancer. Let's see what are the various values this column contain. It contains only the two values, 357 of benign cancer and 212 of malignant cancer. So let's change this value to M for 2 plus 1, that is a positive class, and B to the negative class 2 minus 1. Let's map this, and let's check it again. It has been successfully mapped. As we know that anything which lies ahead of the classifier comes out to be the positive, and anything which lies behind the classifier comes out to be negative. So we have one negative class and one positive class. We have converted M and B into negative and positive class. So let's let's divide the data into the target, that is a Y diagnosis target variable, into the and the feature variable. So after dividing it, we have removed the diagnosis column from here and have moved it to the target as a target variable, because we have to, that is a classification. We have to predict for the test data, we have to predict that classification. So this would be the feature data set with us. Okay, so let's divide these feature and target data set into the test and train data set. So we have divided into X train, X test, Y train, and Y test data set. Let's check out the mean. Basically this is the important part. Actually checking out the mean is the important part, because here we are basically testing what is a distribution of the two classes in the both data set, in the training data set and in the test data set. As we can see, the mean is nearly same, so there is a equal distribution of the classes of type M and B in the both data set. If it is very different, for example one is 40% and other is 10%, then it is then we have to change the random state. For example, changing the random state will change the type of distribution between in the two train and test set. So we have to adjust the random state accordingly, and we need it approximately to be close, because we need the model to be exposed to the exposed to the good amount of the both of the classes, so that it can learn about both of them. Okay, so let's move to the model building part. Here we are building the SVC model with a C, that is a cost factor. The cost factor here is actually the opposite, which we discussed in the earlier video. We discussed in earlier video that if we increase the C, we are actually increasing the generalization and allowing the model to do misclassification more. But here increasing the C actually making the model doing the misclassification less. So actually increasing the C here leads to overfitting. Increasing the C increasing the C here will lead to the overfitting, and increasing the C, as we discussed in the earlier video, will lead to the generalization. So we have taken the linear kernel here. For the C, I would recommend you to study the documentation of the various implementation libraries, because the cost factor has been implemented differently in the different libraries. So we have to basically check out, to avoid the confusion, we have to check out the documentation. So we basically created the model. We are now fitting the model on the training set and giving the training set and giving the X train and Y train to it. And now we are predicting the Y test. We are predicting the classes of the X test using this command. So let's check out the confusion matrix. As we can see in the confusion matrix, 106 is actually the correctly predicted positive classes. So actually 106 are the true positive. These are actually the malignant cancer and have been correctly predicted as malignant cancer. Similarly, 57 is the benign cancer and have been correctly predicted as a benign cancer, whereas 2 is the malignant cancer which has been predicted as a benign cancer, and 6 is a benign cancer which has been predicted as a malignant cancer. So if we calculate the accuracy comes out to be good, 95% accuracy, but it totally depend upon the business for which you are implementing. If it needs 100 accuracy or 100 precision and recall, then you have to take the decision accordingly. Okay, let's move ahead. Now we are using the K4 validation. So in the K4 validation, it's basically what we are doing. We are dividing the dataset into the five folds, and we are taking the one fold as a we are dividing here the training dataset into the 5 fold, taking one as a test validation fold and 4 as a training fold. And so basically it's a whole lot, I would say a whole lot concept of the K4 validation. So basically here we are using a 5-fold validation. Let's move why we are doing the good question is why we are doing the K4 validation. We are doing the K4 validation because we have to calculate the hyperparameter. Here we have taken C bluntly, we have taken C1 bluntly, but actually we can have a different response from the model, or different prediction from the model, or different output from the model if we change the value of C. So the exact or the good value of C have to be determined by us. We give various values of C and find out with which value of C the model is giving me the good results. So we have done the so we are doing the K4 validation, taking the K4 validation here, so that we could find out which is the best C for the current model. So now after the K4 validation, it says as I have told you that it will create the 5 different models on the 5 different data sets, and here is the 5 different accuracies of different models. Okay, so now we are integrating the K4 validation with the grid search. So in the grid search, we have given our model, that is SVM model, and in this grid we want to check out with different value. We want to check out what is the model output, or how is the model coming, how is model building with different values of C. So we have given very variant values of C. It has been expanded in this data range and had been collapsed in this data range. So let's check out what is the how the model performs with different values of C. Let's plot it. It's working. It's taking some time. Okay, I think we are exceeding the time limit. Actually I have planned it for 5 minutes, but actually we are going to cross 10 minutes for the same. I'm speeding things up. Oh my god. I think we got the result. And so actually we have done the grid search on all these C values, and let's check out the result. So these are the different C values: 0.1, 0.5, 0.6, 0.65, and this is the average test score for each of the c values. For each of the c values we have used a 5-fold validation. So for each of the c values I have created 5 model, and this is the average of the 5 models, as we have as we have seen earlier. So, and this is the average of the training on the training model, the accuracy on the training model. Actually we have used the metric accuracy, so it is actually telling us the accuracy on the test model, accuracy on the training model with this value of c. Similarly with different value of c, as we can see there here. Let's plot this up, so we it would be easy. It is already plotted here. So as we can see, there is a spike in the test accuracy, so around c equal to 1, and again it started decreasing, and again it started increasing. Okay, so this doesn't seems to be a good graph to me though. So I think the best C which comes out to be here is approximately 0.7. If you will look here for the 0.7, its testing 98% is a testing accuracy, and 97% is a training accuracy. Okay, so I don't think this is a good graph to be good graph to say. So let's move to the, there is one more implementation of the linear SVC. There we gave the kernel as SVC. Here we are saying the command is linear SVC. So let's check this implementation out. With this implementation we are able to use RFE. RFE is basically recursive feature elimination. So we found out that we don't need all these 30 features in our model. We actually need we can also work with the 10 features in our model. So actually I have taken the top 10 features which have been told to me by RFE. So I have taken those features and replaced the train and test set with that. And let's run this SVC model again on these features, on these features, and with this cost value. As you can see, we let's plot it up. As you can see, now we have a good plot, I would say. Here around this value, first initially the testing and the training accuracy was very low. As we started increasing the testing and training accuracy jumps, and after a certain time the testing accuracy start decreasing and the training accuracy start increasing. This is actually going to touch 1 and lead to the overfitting. So this, at c equal to 100 we are receiving a overfitted model. At c equal to 0.1 we are receiving underfitted model. At around c equal to 1 we are getting a nice model. When this comes to the peak and start decreasing, we take that hyperparameter for consideration. Okay, I have been pretty quick with this Python code. I have been putting this Python code in my Git repository, which will be available in the details section. If you have any questions or any questions regarding me or this code, you can put it in the comment section. I will try to reach them as soon as possible. Thank you for watching this video. Please subscribe for such more video and hit the notification bell icon. Thank you.